Is that okay? Okay, so today we're going to continue with the material of chapter 2, okay? And I'm going to change a little bit the order of the material presentation, okay? The last topic of this chapter, it's about how to calculate what we call the effective breadth, okay? And before that, I explained how these shear stresses that we have calculated in the first part of the course, how these somehow generate a redistribution of normal stresses, okay? But I'm going to put it on a hold for next Thursday, and I'm going to explain the result. And the result of that is the concept of effective breadth. And why is that? Because you need it to complete the report on the experiments that you performed last week. Okay, so that's for today. And then at the end, I will answer I will explain a little bit about how to do the calculations for the report. And also, I'll say a couple of words about the results of the quiz. That's the agenda for today. Today is Tuesday, June 14th. Before I forget, the first day of classes, I explained clearly that in this course, every piece of homework is obligatory. Obligatory means that you have to complete it if you want to approve this class. Some people get behind, and the problem is that every day you get 20% off. I've seen that some students have not completed homework 2 yet. Okay, you have to do it. You have to do it. The very first day of class, I explained it to you quite clearly. You have to complete all the assignments. You have to complete all the assignments. Okay, so you are smart enough to understand what I'm saying. Okay, let's go now to chapter 2. Can you see my PowerPoint? Full screen PowerPoint, anybody?
Yeah, yes, doctor.
Yes, doctor.
Okay, thank you very much. So this is the contents of chapter 2. And as I said before, I'm going to switch a little bit, okay? I'm going to start with the last subchapter, which is 2.4, and that will help you, or that will present the concept of effective breadth, which you need in order to complete the report, okay? So that's what we're going to be doing today. Just a little change, that's all. And then next week we can continue with the next topic, okay? So this is for today. This is today, it's Tuesday, 14th. Okay, now let's go. These are, well, somebody suggested me during the, there was some days that you came and I had the opportunity to talk to some of you, and some said that there are some terminology that it's a little bit difficult for you because you don't know this. So that's what I pretend to do from now on, okay? So as you remember, I explained at a certain point what the flange means or what the web means, okay? But the rest is basically very well known to you, I hope. Okay, let's go. So this is the concept that we would like to present, effective breadth, okay? And you have to be careful because especially in the literature in the US, you have another term which is effective. People, be careful, effective with. Okay? It's similar, but it's not the same. So you have to be careful. In this chapter, in this class, we are going to work with effective breath only. Okay? In a minute, I will explain the difference. Okay, now, this is a result of the shear stress. Okay? Some authors, they include the word shear lag. Okay, and what it means is that, as you can see here, this is the real stress, normal stress distribution in a beam. Okay, so in this case, I'll try to write here. Let's suppose I have this is lateral load. So this is P of X. Okay, so I have a lateral load in the Y direction. And because of this lateral load, we're going to have this and that. This is V of X, this is shear force, and this is the bending moment, okay? Now, if we apply our bending theory that you learned in previous courses, how do you calculate sigma X? Anybody? Or no, not anybody. Is Sigüenza, how do you calculate the sigma, the normal stress in the case of beam bending? Remind us. Miss Sigüenza, please, Isaac, we're going to be radical. If I ask something and that person doesn't respond, take him out of the session because they are making us waste time and I don't want to waste time. I'm done with that. Okay, so somebody doesn't answer, take them out. That's as simple as that. Okay, go on, Ms. Sigüenza. How do you calculate the normal stress in beam bending?
Okay, Bx.
This is normal stress, Ms. Sigüenza. No? Ms. Poveda, are you there? Ms. Poveda, how do you calculate sigma X in beam bending? Ms. Poveda? Ms. Poveda? Don't make me waste time.
The moment times Y over inertia.
Exactly. So that's mz of X, Y divided by the inertia I sub C. There's something that we're missing, Mr. Villalba? Something we're missing here, Mr. Villalba?
The sign.
Yes.
Sign.
Don't forget that. Okay, now, from what point do you measure Y, Mr. Vasquez? From what point do you measure Y? What is the origin of this system? Mr. Vasquez?
It is the point from the neutral axis to the...
And what is the neutral axis?
In this case, it's gonna be...
No, in this case, in general.
In general?
Yes.
Is when the stress...
No.
Is where...
No. Zurita, tell me, where is this point located?
Good morning, doctor. And finally, wet.
Come on, Mr. Guaman. What is this origin located? Come on, it's not that difficult.
In the middle of the plane.
The centroid.
The centroid, yes, the centroid of the section. Okay, now we're cooking. Okay, now, if Y on the flange is the same, we'd expect, applying this formulation, that any stress, any normal stress on the flange had to be the same. But we can see in this figure that it is not, okay? And it's not because the presence of the shear stress, okay? So oh, Jesus Christ. Okay, this is the shear stress according to this expression. So since the flange is at a constant distance from here to here, for all of this flange, the y distance is the same. That means that the stress, the normal stress, they should be constant, but it's not. And that's because of the presence of the shear. So in this case, we want to calculate, of course, the sigma max. Why? Because sigma max is the largest value, and we are interested in knowing if this value, the maximum stress, is close to the allowable value. If this value reaches 235, in the case of the steel, we're in trouble because there will be a permanent deformation of the beam. See? So the mean value is this one here, is the value that we obtain after applying this expression, but this distribution, okay? In the connection with the vertical element, we have the largest value. Okay, so how do we calculate this? Well, that's the, or to determine this, this parameter, the maximum stress, we apply the concept of effective breadth, okay? And this is the result of the research of a professor at the University of Berkeley. Okay, his name is Shear. I will present some information from him in a minute. Okay, so what does he say? Okay, originally, we have this distribution of normal stress, okay, which is the real distribution, okay? Now, if we integrate this, okay, we're going to have a net force acting on the flange, right? This net force, combined with the forces on the web, produces this bending moment. And remember that bending moment has to be exactly the one that we need in order to have equilibrium. Okay, now, instead of this distribution, which is very complicated to determine, okay, what we do is we assume that in this region, see, from here until here in the flange, we have a uniform distribution of stress equal to the maximum value. This value is the one that we try to determine, okay? And of course, since we are applying here in this region, you can see that we're applying more stress than the real one. We have to reduce this by a little bit, so that if we integrate this stress on the flange, we will have the same contribution as the original stress distribution, which is this one, right? So we still recuperate the value of the bending moment, and we are still in equilibrium, okay? So to do that, this is what we do. Okay, on the left-hand side of this equation, we integrate the stress, okay? So we have sigma, and this is the differential area, okay? So this will give me the force in the axial direction on the flange. Okay, now, instead of this, because this is very complicated to calculate, we're going to take this fictitious distribution. In this case, the sigma x max is constant, okay? So we have to multiply that times the area. And this alpha is what we call the effective breadth. Okay, and you see immediately that lambda, the effective breadth, is a little bit smaller, lower than B, which is the real B, the real breadth. Okay, now usually the thickness on the flange is constant. Okay, So we can cancel from each side of this equation, and this is the expression that we use in order to calculate lambda, okay? Now, some people think is, why do we need to do this? I mean, yeah, the problem, you will see that in a minute. Why Shady, which was the person who developed this concept, had to do this quotient in a minute, okay? So we integrate, in this case, in this direction, there's something, there is an error here, because this is the z, this is z, because we are integrating in the z direction, okay? So, and this is also incorrect, this is z. I'm sorry, okay? And this is the maximum value of the stress that we're going to eventually estimate. So what Shady does is he presented a procedure to calculate lambda, okay? Once you calculate lambda, it's like having a reduced flange beam, okay? So once you reduce the breadth to the effective value, which is lambda, you recalculate the inertia. With the new inertia, you can calculate the sigma max, okay? So this is what the procedure on the right-hand side I'm going to write first, okay? We will apply this in the last chapter of this semester. So you calculate lambda, calculate inertia, effective, and for this calculation, you do not consider this part, only the effective part. And finally, calculate sigma max. Okay, that's the procedure, people. Okay, now we're going to explain how to calculate lambda using the procedure from Shady. Are we clear, people? Are we clear? In the quiz, I asked you to calculate the inertia, and there are some problems there. Okay, we will comment that at the end of this session. Okay, so we calculate lambda. So in this area, in the lambda part of the flange, we assume that sigma is constant. Okay, after we do this, we calculate the effective inertia of the section. And with the effective inertia of the section, we can calculate the maximum stress. And this is the value that we need, right? Because this is the value that has to be compared with the allowable stress, okay? So how to calculate lambda? That's our problem, okay? So this article, as you can see here, it was written a long time ago, 1952, and it's called Effective Rate of Stiffness Plates Under Bending Loads. Let me go back here. You see that this is a problem where you have lateral load, and because this lateral load, shear force and bending moments are required in order to have equilibrium, okay? I mentioned okay, and when we say bending, that's what he called it, under bending loads, okay? So effective breadth is related to bending, okay? When you talk about effective width, that's buckling, okay? This is the society that I mentioned last week, SNAME, okay? They produce a lot of information, they collect a lot of information. They usually organize meetings every year and things like that. And this is a typical publication of them, okay? they published these transactions. It's a collection of articles, papers, and they presented in a single book. Okay, this was presented in 52. Okay, now, what's the problem here? I'm going to give you a brief summary of how Shady faced this problem. Okay, so let me go back again. So here, let's think that the flange, okay, only the flange, okay, it's a plate, and the plate is subject to in-plane forces. Okay, so because of the bending, we have this bending moment, and the bending moment generates in-plane forces, in-plane stresses on the flange. Okay, and that's the problem that we are going to be facing here. Okay, so let's consider that this is the flange. Okay, and we have X stresses, Y stresses, and also shear stresses. Okay, so there are no stresses in the vertical direction. Now, if this is the thickness, okay, we assume that in the thickness, since it is very small, okay, the stress doesn't change. Okay, so if I go up in the thickness, the sigma doesn't change. Okay, sigma X, sigma Y, or tau XY, they don't change in the thickness because we assume that the thickness is very small. Okay, so this is what we call an or a plane stress problem. See, you see here, plane stress problem. Okay, now, of course, we can take a small piece and make summation of forces in X equals 0, summation of forces in Y direction equals 0, and summation of moments. People, if you do summation of moments, what are you going to get? Mr. Llanos from solid mechanics, do you remember what you obtain if you do summation of moments around the Z direction? Mr. Llanos, do you remember? If you do summation of moments, what do you obtain?
Good morning, doctor. Summation of moments.
Yes. What will you get after you do summation of moments? No?
No, I don't remember. Sorry.
Okay, good.
Yes.
Miss Leon, do you remember what do you obtain if you do summation of moments from solid mechanics? From solid mechanics, what do you obtain, Miss Leon?
No, I'm not sure, Miss Doctor.
Okay, no idea. Anybody, people? Anybody? Anybody?
Summation of moments equal to 0.
What will you get if you do that in this case?
Equal to 0.
No. So if you do this, something like this, you take summation of moments. What do you obtain? Tau XY
Tau xy
equal
to tau yx.
exactly. So that's there. Okay, now this is the way we treat plane stress problems. Okay, we define a new variable. Okay, this is phi, and this is what people call 80 stress function. Okay, so this is there is an error here. This is the definition. This is the way we define the 80 stress function. Now, if we do this and plug it into here, you will see that this equation of equilibrium are completely satisfied. Okay, so if we define phi in this way, equilibrium equations are completely satisfied. Now, usually, up to now, we try to solve equilibrium equation, right? And trying to solve equilibrium equation, we find the solution of our problems, okay? Deflection and differentiate that, and we got moments and all of this. But right now, we are saying that defining phi in this way, we satisfy this. So we need another equation in order to solve this problem, okay? And this problem is what we call the compatibility equation. It's a very long name, compatibility equation, okay? If you can see here, okay, this is a relation, an identity, okay? If you differentiate twice this derivative and add to the second derivative of du dx, it's exactly the same if we do this. It's exactly the same, okay? You see here that you have the third derivative, 2 in x and 1 in y of v. And this is what you have here, 2 in x and 1 in y. And this one here is the third derivative of u, 2 in y and 1 in x. And this is what you obtain here, okay? And all what we're doing is just changing the order of differentiation. Now, if u and v, okay, if u and v are continuous function and differentiable, you can alter the order of differentiation. So we are fine. But you can identify this thing here. Mr. Kimi, Elvis Kimi, what is this? What is this term? Mr. Kimi, Elvis Kimi, what is this term?
No, sure, doctor.
Ah, come on!
Deflection.
No! dvdy.
Slope.
More than that. Come on, people. This is epsilon y. And this thing here is epsilon x. And this thing here, what is this? Mr. Dominguez, what is this? Mr. Dominguez, what is this?
Epsilon y plus epsilon x.
No, no. This is du dy. du dx is epsilon x. This is du dy plus dv dx. Mr. Soria, what is this? Mr. Soria?
Epsilon C.
No, no.
Maybe sigma.
Gamma xy, gamma xy. People, come on. You have a very good vacations. You remember these things? Gamma xy, yes. Now, the thing is this, okay? You can relate, as we can say here, this, we can relate this to Hooke's law, okay? So let me erase this. All what I'm trying to do is trying to explain in a very, in a summary, what Professor Shady did, okay? Remember that you have epsilon x, epsilon y, and gamma xy, and you relate that to sigma x, sigma y, and tau xy. Because these are the stresses. See, I'm going to include only, these terms here. Because the other, in the case of plane stress, we said that this, or all the other terms are 0. Sigma z, tau xz, tau yz are 0. So these are the only one that we have, okay? Do you remember what do we have here in this location of this matrix? Anybody?
1 divided by John's modulus.
Yes. And here, anybody? Minus
0
divided by E.
Divided by.
What do you have here in this location? Anybody?
0.
No, it's 1 over G. This is the shear modulus. It's similar to the Young modulus, but it relates shear stress to shear strain, okay? And for a isotropic material, remember that G is equal to E divided by 2, 1 plus nu. What is nu here? Anybody? What is nu?
Poisson ratio.
Poisson ratio, yes. So when you pull something, right, it elongates in the x direction. but it reduces its length, thickness in the y and z direction. You calculate that using the Poisson ratio, okay? The contrary also is true. If you push, you will compress something, right? It will expand in the y and z directions. Now, that means that here, instead of epsilon y, I can relate it to sigma x and sigma y. Similar, this one here, I can relate it to sigma x, sigma y. And this I can relate it to tau xy using the Hooke's law. But now we have the definition of the A's stress function, which is here. So we can take this and replacing here. All of this expression for tau can be replaced by the derivatives of phi. And at the end, you simplify, and this is what you obtain, okay? And this is what we call one of the compatibility equation. This is typical for plane stress problems. So this is a fourth order linear partial differential equation. Don't worry, I'm not going to solve it. I'm just going to summarize what Shady did. That's all. Okay, this is typical of any plane stress problem. So this is the fourth derivative of phi with respect to x plus combine it. And then the other term is equal to 0. Okay, this is the same as this one here. And we have now to try to solve this equation for the flange, okay, for the flange of the beam. Now, let's continue with what he did. Okay, so this is what we are looking at. This is the flange. So this is x, and this is going to be y. Okay, and we are only considering this. Okay, and we have stresses acting along the x-axis. Okay, so we are taking only the flange of the beam, and we are considering that as a plane stress problem. So this is the equation that you're trying to solve. Okay, if we find phi, then we can go back and we can apply the definitions of the A's stress function and finally calculate the distribution of stresses. Okay, if you find phi, you calculate sigmas and taus, and you can also determine if you are safe or not. Okay, now what he did was he proposed a solution. Okay, here he said that in the x direction, the dimensions are usually much larger than in the y direction. So in the x direction, variation are softer, I mean slower. The variation of the function is slower in the x direction compared to the y direction. So he assumed this distribution, this variation in the x direction. In the y, he tried to solve it. Okay, now in this case, omega is defined as this one, with L is the length, the total length of the flange. See, from here to here, this is length. L. Okay, now he replaced this into compatibility. Okay, and make some simplification. And oh man, let me list this because you cannot read this. Please don't write on my screen because it confuses me. So this is the x direction. Okay, so this is the solution. Okay, you can see here that this is a fourth order equation. So here you have 1, 2, 3, and 4 constants. Okay, so it's like we have done so far in our class. Okay, every time you integrate something, you include a constant of integration. Basically, you have integrated 4 times. It's like similar to having to include 4 constants of integration. Okay, so I think this needs a sub n here because this is one term of this expansion. Now, that's the problem. Why? Because in the problems that Shady wanted to solve, he had only 3 boundary conditions. Okay, so he could determine only 3 of these constants. Okay, or in other words, he can express 3 constants as function of the last one, usually as a term of A. Okay, so these are the 3 problems that Professor Shady tried to solve. Okay, so first, this is what we call case 1. It's the case of a single web. Okay, it's like a T. Okay, this single web basically like a T beam. Okay, in this case, this is a flange, and you see here, please, you have to be careful because this is the notation that he employed. Okay, this is the original from the original work. Okay, so this is from the article that I had a copy of that. Okay, so B, you can see here, little b is half of the total breadth of the flange. Okay, now here in the central part, you have symmetry, right? So this is little v, so there is no motion, there is no displacement in the y direction because there's symmetry. There's a symmetry plane. So v is 0 along this axis. Okay, now this is a free edge. So in this direction, that's sigma y, since it is free, you can say that it is equal to 0. And also, since it is open, this tau is also 0. Anybody, could you give me the subindices of this tau? Mr. Chikaisa, can you give me the subindices of this shear stress element?
Okay, the subindice is
On this axis.
okay, x.
Oh, what? I'm sorry?
X.
X.
Right.
Come on, man. You have to give me 2 indices if this is tau.
Okay, yeah. If x
This is the no, I'm wrong. This is wrong. I'm sorry. This is a positive edge, right? So in this case, this is the tau. It's the card is perpendicular to the y-axis, so this is y-x. Okay, so on this edge, you have that this is true. And this thing here, v is 0. But there are only 3. On this edge, you have only sigma y and tau is equal to 0. So you see that we are missing one boundary condition. Okay, and what we did was he applied these 3 boundary conditions, and he determined C and D as function of A. Okay, so all the problems that he solved are symmetric. Okay, so after doing that, he found a relationship, and then all the 3 cases have the same variation. And then with the other 2, these 2 boundary conditions, he expressed C and D as function of A. But also, that's all what we can do because we have only 3 boundary conditions. Okay, the second case is this one here. If you see from the front, it's something like this. Okay, so this is a web, this is another web, and this is the flange. Okay, so it's a double web case. Okay, in this case, again, you have on the center, you have a symmetry axis. So again, there is no displacement in the y direction. And you can remember from the chapter 2.2 that since this is symmetric case, okay, in this point here, the stress, shear stress has to be 0. Why do we need here to be the shear stress equal to 0? Mr. Medina, Williams Medina, why this shear stress has to be 0 in here? Mr. Medina.
Yes, teacher.
No?
No, no.
Miss Jurado, why this stress has to be 0? I'm sorry, in the symmetry axis. Here, why it has to be 0? Miss Jurado, are you there?
Yes, doctor. Is equal to 0 because these two will be simplified.
Some. Remember, if you have a force pointing to the right here, you need another force pointing to the left in order to cancel these two, because we have only forces in the vertical direction. There are no forces in the z direction in this case. So in the symmetry plane, we need tau to be 0. So we change direction. This is pointing in that direction. We change and we start pointing in the other direction. Okay? So the two actions cancel out and we have no net shear force in the z direction. Okay? Okay, again, you can see that we have 3 boundary conditions. Okay? And we can determine 2 constants as function of the last one here. Okay? So we can express everything as function of a sub n. We can never find completely the concept of integration. The third case, it's more useful to us, okay? It's a case where you have multiple webs. For example, let's suppose that this is a plate, right? I don't know, you see this is the deck. And you see, for example, deck frames, okay? These are deck frames, okay? So each one of these, okay, is our case, okay? And you see here is that this is the web, this is another web, and you locate the origin in between these 2 webs, okay? So again, you have symmetry, so the deflect or the displacement in the v direction is 0. Again, you have symmetry, so the tau is 0 here, and also here you have symmetry, so you don't expect this element to deflect in that direction, so v is also 0. So again, we have 3 boundary conditions, so we can express C and D as function of A. So you see here, C as function of A, D as function of A, C is 0, D as function of A, C is 0, and D as function of A. So that's all what we can go so far, because we have only 3 boundary conditions for each one of these cases. Okay, that's, I guess, I wasn't there, but I guess that's the point where Professor Shady said, okay, I cannot solve this, right? But what I can do is I can set a quotient like this one here. If I make a quotient here, I can take one constant outside the integral. It's the same constant I have in the denominator, and I can cancel and I can evaluate. Okay, so following Shady's theory, we are not able to completely determine the distribution of stress. But what we can do is we can obtain a ratio between the integration and the maximum value. And that's the effective breadth. Okay, that's, I mean, I suspect, I never met Professor Shady to talk about this, but I suspect that's what he reasoned, okay? So he had 4 constants of integration, only 3 boundary conditions, and the only thing that he could do is somehow define a quotient, okay? So with this quotient, he eliminated the last constant and he was able to evaluate partially the result, okay? So you will never, following Laplace's equation, you are never being able to calculate completely the distribution of shear stress, but applying the concept of effective breadth, you are able to calculate the maximum stress, which is something that we want, okay? Following his theory, okay, he calculated lambda sub n. We have to be careful with this. This is just sub n, okay? So lambda sub n is the result of the integration of sigma x n, one of the constants, dy, and divided by sigma x n max. Okay, so with these two, he can cancel the a sub n and calculate this term here. Okay, completely. But he doesn't find a sub n, he finds a ratio of these two things. Okay, this is the integration from 0 to b. Okay, so this is for case 1, when you have a single web. He also presented the solutions. This is the solution for case 2. No, this is the solution for case 3, where you have several webs, okay? There. And once you have that, you remember that you had an expansion, a series expansion. So he replaced all of this in the solution, and finally he was able to find a value for lambda. You have to be careful. This is lambda sub n, and he was trying to find, of course, lambda. So if you include several of these terms, eventually you can able to find lambda. As you can see here in this figure, they tend to a small value. Okay, so they tend to 0, both. That means that if you include enough terms in the expansion, okay, you can cut the expansion and assume that the rest is not that important. It's not that enough. So I did this calculation, and I had to include, well, not 1 or 2 terms. I had to include more than 10 in order to have an acceptable error, okay? But that's something that we can do easily with the computer. But anyway, is there any questions about this process so far, people? Any questions about this process? It's like giving you a short story, okay, about how he solved this procedure. Okay, now, what's the solution of this? Well, he presented his solution in the following way, okay? This is something that you have in your class notes, okay? Here, he found that he related the lambda, he related to the, if you plot here, the bending moment, okay? So here you have a beam, you have the loading of on the beam, okay? So you can do a cut at any point and draw the distribution of the bending moment. So for example, let's suppose the distribution is something like this, okay? So you see here that there is a point where the bending moment is 0, 0, and 0. Okay, so this distance, he called it C, little c times L, okay? So, of course, this CL depends on the distribution of the load, okay? This depends on the P of X, okay? So, according to the loading and according to the supports of the beam, you have the distances between points of 0 bending moment, what we call CL, okay? And he divided by, this is large B, okay? So this is CL divided by large B. Okay, now, and according to the cases, you have here the cases, okay? You found the ratio between lambda and B. Okay, lambda is the effective breadth. And B is just the breadth. Okay, and you can see here that there is some problems with the theory because here you're saying is that the effective breadth is higher than 100%. Okay, so usually the maximum value that we take is just 1. Okay, makes no sense to have more material than the one that we have physically. Okay, and these curves depends on the type of load that you have. Okay, so if you have uniform load, you use this this curve. If you have B, sinusoidal load, etc. Okay, and this beta is a factor which depends on the geometry of the section. Okay, and it's combined with the central load. Remember, when you have a central load, you have a very extreme situation because you have to apply a delta Dirac, and that means that things change radically at the point of application. So that's a very special case, okay? So and this beta factor depends on the geometry of the section, and this is defined, okay? Don't worry, we are not going to use, well, we can use some of these, but I will show you some more practical way to evaluate this, okay, in a minute. Okay, if there is no questions, then we're going to take a break, 5-minute break, and when we return, we can say a couple of words more about this, and then I'm going to show you how can we find up to date, because this material was developed in 1952. That's a long time ago. Right now, the classification societies bring us this information with more up-to-date techniques. So you'll see there is some relation, but it's not quite the same, but it's similar. So basically, that's why I wanted you to know something about this, the theory of Dr. Shady. Okay, so let's take 5-minute break, people. We can stop the